Hello everybody, welcome back to my regression analysis videos. Alright, let's get right into this. What we have here is a data set of a local resort town that wants to analyze the relationship between the size of a one-bedroom apartment and the corresponding rent. So the idea, bottom line idea, and I always like to start there, is this X predicts this Y. I always want to know what we're predicting, because what we're predicting is my outcome variable, my Y variable. And that's extremely important when you move on to advanced statistics and have multiple X values and do multiple regression. Check out my other videos on multiple regression to see what I'm talking about. All right. In this case, we have one input and one output. So it's very important to know what your input is and what your output is. And that's called reading the question carefully. So we want to predict the rent given the apartment size. Got it. So what do we do when we have two variables and we want to predict one? One nice option is called regression analysis. So let's get right into it. We scan in the values, insert, recommended. Hopefully the scatter comes up. Nice. If scatter doesn't come up, go to all charts, pick scatter. And so I'm going to drag, you know what? Let's bring it up too far. Let me bring it up and over so we can see the scatter plot. Let's bring this over a little bit so you can all view it with me. So we have our scatter plot, and you should label correctly. You can add X and Y details if you're going to copy and paste this into PowerPoint or to Word. I just want to look at the scatter plot, and I want to ask myself, does adding a trend line that is linear a good idea? So we look at linear, and it looks like it fits really nicely. There is some scatter in here, so I expect some error. So my R-squared is not going to be too big. But overall, the dots are pretty close bunched around this line. So I'm okay with a linear prediction. So I'm going to click on Display and display R-squared. At any time that I'm going too fast, you should pause the video and try to figure out how I did this. I'm doing this faster because this is probably the fourth video in the chain of regression. All right, so by now, if you've gone through my 4 videos, you've seen what I've done in detail. So the first thing I always do is I check out the picture and I see if it makes sense to do linear regression. See, if there's a major bend in the data, I wouldn't do linear regression. I'd come up with a different type of model, a nonlinear model or a transformation to make it linear. I got some cool options for nonlinear models. See future videos on that. Because of this information, I honestly can get the equation right away, right? The slope, 0.4932. The y-intercept, 0.1255. The r-squared, as a percent, 12.55%. So I have all this information at my fingertips because of what I just did. I will look at these later because I don't trust these values until I run my analysis, my 4-point analysis on my data set. So what is the 4-point analysis? Well, that's called the residual assumptions check. To do that, you go to data, you go to data analysis, you go to regression. If at any point you're missing something, you got to go back and you got to put it onto, can't scroll back. So first, I'll move back to my data so I can work with it. Data analysis regression. I need to scan in the numbers for the X, and this is why, and the Y, and this is why it's important to know your X and Y values. So there are my Y values scanned in, and so then my X values are here. And in Excel, I would always recommend you putting your X on the left, your Y on the right. It just works so much smoother in Excel that way. So I got my Y and X loaded in, checked them to make sure I did it right. I didn't highlight the label, so not clicking there. I want these 3 things checked: residuals, plots, and norms. I need those checked. Where I put my information, I always pick a spot, and it's always the same way. Bottom and to the right, it's empty because it's going to dump a lot of information. Click OK, and we get some really interesting information. We get the residual plot, we get the norm probability plot, and we get this residual analysis that I'll utilize in a second. So the line check, L-I-N-E, linearity. How does one check for linearity? Well, you check the picture. If a line looks like a relatively good choice, Linearity is check. You can also check the residual plot. If any significant pattern develops, linearity might not have been the option. See, this is kind of a check. The residuals are the errors in your prediction. That's what a residual is. A residual are your errors in using the prediction line to make predictions. So when we do this prediction line, the residual is your error plot. And if you made a mistake, and you said, ooh, this is a good model, hopefully the errors would pick that up. Like if there's a major bend in the errors, most likely I can go back to my picture and go, oops, I missed this bend here. Oopsie, I should not use linearity. Again, I'm thinking linearity looks good, and honestly, this ball is awesome. And let me do equal variance while I'm here. Equal variance states as I go across left to right in my residual plot, there's no growth or decay in the scatter. Well, the scatter roughly stays the same height. That means when I build my confidence intervals, I'm happy. I want equal variance because I want to trust my confidence intervals. I don't want, as I go left to right, my confidence intervals to expand or to decrease. I don't want that. I want a nice equal spread as I go left to right, and I have that. So not only do I have the linearity check, I have the equal variance check. Again, the equal variance is looking left to right and making sure there's no growth or decay in the residual plot. I can also do the NPP plot. See, the normal probability plot takes our data and puts our data into a one-to-one plot against where it should fall in the normal distribution. If my data points fall roughly in a normal distribution, this line would be roughly horizontal. And this line, not horizontal, but linear. I mean, it looks like a line. I don't care if it's increasing or decreasing, but it looks like a line. If there's a major bend in this graph, then once again, well, two options. Either I have what do they call it? Outliers. Lost a vocab word. Either I have outliers or I have a nonlinear part that I have to deal with. I don't have outliers. I don't have a nonlinear path. Everything looks pretty straight across. So my normality holds true. Why do I care about normality? Come on, guys. Look back over here. When you're running a t-test, you need to make sure you can use the t-distribution, which is normal. The equal variance covers the confidence intervals. I'm doing all these checks, so all this report that comes out of most standardized advanced statistics packages are true. Everybody has to check the distances, check all these details. So linearity, yes. Since my residual plot has no pattern, I'll check that out. That should have been down there. I apologize. So that, yes, should be down there. Yes, since my residual plot has no pattern. If there was a pattern, I think my linearity would be violated, and I probably should do some nonlinear transformation or something of that nature. Second, independence. I'm going to assume, in this case, when they collected the data wasn't collected quarterly. If the data was collected weekly, quarterly, monthly, like every week, every quarter, then there's an issue with a time component. There's an issue with which the data is collected. One result could hinder or grow the next result. And as far as I can tell, the data has no issue here. But if you're worried, you can run a Durbin-Watson test, an advanced test, and you can look at my future videos on Durbin-Watson to analyze utilizing Durbin-Watson. If I'm running the Durbin-Watson, I'm going to a more advanced package, RStudio. It's awesome. It runs the Durbin-Watson quick and easy. Same idea. If I'm worried about outliers, let me just mention outliers. If I'm really worried that I might have an outlier, I'd run Cook's distance. And you can check out my video on Cook's distance for outliers, and I would utilize RStudio again. There are just certain times when you got to stop playing with Excel and move on to advanced packages that do it quickly for you. Durbin-Watson and Cook's distance are done quickly in RStudio. So I recommend that if you want to really, really firm up your assumptions. If you're really worried about independence as a factor, then you run a Durbin-Watson. If you're really worried about outliers, you can run Cook's distance. By the way, those are my suggestions. There are other suggestions besides Durbin-Watson and Cook's distance you can read about in advanced statistics courses. See, we're attacking this problem from a very low-level, basic-level statistics course. And so that means it's all visual scans. Linearity, check your residual plot. Are there any patterns? No. I'm pretty sure linear works. Independence. Look at the way the data was collected. Do you think there was a time component? Do you think there was a component interference? Not really. Normality. You check the NPP, and I see a line. And that's awesome. If you don't see a line, you see a major bend, you're in trouble. Probably a transformation or an outlier you got to deal with. Equal variance. The residual plot has no growth or decay. So you're good again. If there was major growth or decay, I'd worry about equal variance, and then I have an issue with my confidence intervals I want to build later. These are my assumption checks. You have to run them before you get to state, ooh, this is nice, ooh, this is not nice. You have to verify that your model is accurate, and that's what these do. After you've done that, then you can have fun. You can talk about, all right, now that I've verified for the most part, things look good, here we go. Let's get into it. The slope. What does the slope mean? Remember, slope is change in y over change in x. So the way I look at it is a 1 unit increase in x. So just tell me what x is. Well, x again in this case is what? Square footage. So for every square foot, there is a rent increase of 49 cents. Y, which is 0.49. And that's how I always represent my sentences. For every increase in x, this slope tells me the increase in y. For every 1 unit we go in x, this is the increase in y. So we're paying 50 cents per square foot. That's what we're paying here. We're paying 50 cents per square foot. Or roughly, not roughly. So 49 cents per square foot. All right, so that's the slope. As I mentioned before, the y-intercept doesn't make much sense unless you have data close to it. Again, I heed my warning. If you're predicting past your data, you're getting into areas in which your errors have not been checked, your residuals have not been checked, and so I don't trust my prediction line as much. You can predict out this far, and people do. That's why they're called predictions. But until you have data out here, down here or above, you are at the whim of maybe there's a major bend here, maybe not. So when I say the y-intercept, I'm talking about right here somewhere. The y-intercept is 0.1255. Kind of interesting. The graph of this, the y-intercept would be 0.1255 because that's not the y-intercept. Sorry, guys. Let me read the y-intercept. 992.99. All right, this is a great time, right? 992.99 is the y-intercept. I read r squared. I apologize. The y-intercept is 992.99, and that makes sense in the graph. Look at the line. It's floating to about 992.99 if I extended this graph. That makes sense. Now, typically the meaning of the y-intercept is not the most useful. So what is the y-intercept? It's when x is 0. X equals 0. What does that mean here? That means no square foot, and the rent is $992.99. So this is hey, welcome to the resort town. Here's a beautiful 0 square foot apartment. I have no clue what that looks like. A 0 square foot apartment, and you just got to owe me $1,000 a month. Woohoo! Sounds like a great deal, doesn't it? Yeah. Okay, again, just a warning of predicting outside the bounds of the data. If you watch enough of my videos, and if you do enough of this, there's certain protocols you adhere to when you look at these. They mean something, and you got to be able to explain them. If you're putting this picture in your PowerPoint, better be able to explain these 3 numbers because people are going to come after you. And so having a good understanding in the limitations is extremely important. So what's r squared? To me, that's an important number. 12.55% of the reason y, whatever y is, in this case, what is y? Y is the rent, varies. So I'm giving you a big reason, 12.55% of the reason y varies is due to the variation in apartment size. I'm actually kind of amazed by this. I only have 12.55% of the reason. I'm actually very amazed by this. But hey, that just tells me there's other variables out there that are more important to my investigation. There are other variables that contribute to this resort town than the apartment size for why the rent varies. I do have 12.55% of the reason, and to some people that might be good. I'm looking at the multiple R right now, and I noticed the multiple R is 0.35. That's your correlation number, by the way. So it's not the strongest. So I know my predictions are not the strongest. So I can predict they're just not going to be that good. I can predict they won't be that good. Why won't they be that good? Look at your multiple R, 0.35. And as I stated before, if you're inside of negative 0.6 to 0.6, your correlation that is, then you are looking at a very weak type of prediction status. So we can predict. Believe me, I have the prediction line right up here. Just plug in your X, plug in your square footage, and off and running. We are going. We can definitely predict. It just won't be that strong. But we do have 12% of the reason. That's good news. Because who knows, another variable we pick might be smaller than this. I call it the family feud. 12 people might have said, woohoo, number one answer might be 12%. There may be another bigger answer. I don't know until I investigate other variables, right? You try another variable besides apartment size. Maybe you try fees. Maybe you try amenities. I don't know. I don't know what we're looking at here, so I need other variables to dummy up. But in this, what I know right now, currently, is if you're looking at the apartment size, it's 12.55% of the reason rent varies. So I do have some of the reason. I just know that 88% of the reason is still unknown. All right, can you build a slope? Well, yeah, you can, and there's a formula for it, by the way. You can, I don't think I'm a formula sheet, nope. But you can get the formula. I state we are at the point now where we have technology, and the technology does it for me. You just got to know where it is. 0.1, what is that, 0.7, comma, 0.879, so 879. Where did I get that? From this information right here. The x-intercept, the x variable is known as the slope. So the confidence interval, the 95% confidence interval for the slope is right there, already built for you. If you have the formula, I ask you to try to take the formula and get those numbers. You should be able to take the formula and get these numbers right here. Of course, if you're just looking at here how to build these quickly, this is where Excel comes in great. It's right here. By the way, my next question involves hypothesis testing, and there's my hypothesis testing numbers. My t-value is right there, 2.57. My p-value is 0.013. All right, I will discuss all these now. So what do we got here? Well, remember, we stated we have no growth, no decay, which means my confidence intervals are good. What does this confidence interval do? Well, what it does is I have a 95% confidence that true slope is between those values. What does that mean to me? It means in terms of business, because remember what the slope does here. This is your sample slope. This is a 50%, let's say it's 50%. That is 50 cents on every square foot. 50 cents on every square foot. That's really what it is. For every square foot we increase, we could charge another 50 cents typically. What if we now are building a brand new condominium and we want to increase the price because we believe we should be able to increase the price off of this base price? Well, you can utilize this slope. You can utilize this confidence interval. See, I have 95% confidence that if I looked at every single apartment in this resort town, the true slope would be somewhere between these two numbers. Where between these two? I don't know. Do not say in the middle. That's bull crap. That is basic rule 1 bull crap. Rule 1, the sample slope is always in the middle of the two. So don't even go where the population slope is. The population slope would be the slope if I had all the resorts all calculated out. I don't have that. Let's say there was at least 5,000 resorts in this resort town, and I could no way get into that data. All right, so what I mean is I do a sample. Got my sample, because we almost always do a sample. We hope through a good sample, we can expand out to the population. So back to the story. The story is all about charging rent. This is where having a confidence interval plays the game. If you know the typical rent is 50 cents per square foot, but you believe you're building a brand new hotel, it has gold-plated toilets, woo! Then why not charge a little bit more? And you can. And people can't say, oh, you're price gouging. Nope. As long as you charge up to 88 cents, you're good. You might be saying, oh, that's not that big deal. Oh, heck yeah. I mean, that's an extra 40 cents per square foot, all right? And if you have a large apartment, this could be a couple extra $100 a month. There could be a major change in price based on the fact you increased it. Are you allowed to? Heck yeah. Because again, what is a confidence interval? It tries to capture the true measurement of the slope in this case. That's what this is. Confidence for the true slope. See, you have your sample slope. This is based on your sample. But your samples vary. I can add and take away a number based on a new resort, and that changes. I want an idea of where the true slope would be, and that's where this is. By the way, you could look at the lower end also. If you feel you want to be cheaper and you want to go low, but you don't want people, the other apartment guys mad at you for under gouging them, right? Like, come on, man, you can't price this out of the business. You can charge down to 11 cents. Right? You could charge to 11 cents, take 30 cents off per square foot, and still they can't complain because you can say, hey, I built my confidence interval for slope based on these apartments, these condominiums, and I can go as low as 11 cents and really be close to the true slope. We don't know where true slope is, so they cannot complain because you have built a 95% confidence interval where the true slope is. Awesome. And this is where we utilize this in business, is we look at the typical predictor, but if you think you're going to become in a big, more impressive product, replace it with a higher slope. Higher slope means a higher multiplier in the prediction. If you believe you want to go to a cheaper route, you can replace it with a cheaper number. Instead of multiplier by 49 cents, you could multiply it by 10 cents and 7 cents. All right. This is why we build the confidence intervals. But I can't believe the confidence intervals if I don't believe in the checks, right? It all comes down to I believe this check, which means I believe the confidence interval. Got it. Now, I did do the normality check. The normality tells me the t-test will be accurate. If the normality check varied, then I wouldn't believe the t-test. Why do I care about the t-test? Well, again, it all comes down to, do you believe in your prediction line? I want to make predictions. Do I believe in this prediction line? Well, what I can say is, I can assume, worst case scenario, the slope is 0. If my slope was close to 0, that's a bad prediction. That means your slope, your line is horizontal. And that means there's no relationship between these two. If you have a potential prediction line that's horizontal, that means they're not useful predictors of one another. So let's assume it's 0. So what do? You run a hypothesis test. What are the steps in a hypothesis test? You get your t-statistic, you get your p-value. And then you check out your p-value. Well, this p-value is 1.3%. So this, you got to be careful. It depends on your alpha, right? You usually set down your alpha. If alpha is 5%, which is the typical one, the Freudian alpha, if alpha is 5%, then we would reject H naught because p-value is under alpha. If p-value is under alpha, we do reject, okay? And that's H naught, and not H smiley face, H naught. We do reject H naught. So I know my result. We reject here because my p-value is under 5%. If your alpha is 1%, you're going to say I do not reject. See, this is the slippery slope here. This p-value is 1.3%. So we call that 2-star significant. If it was under 1%, it would be 3-star significant. See, a 2-star significant means your alpha is 5%. It means your p-value is under 5%, which means, in my case, typically I use 5% as my threshold. I would reject, which means I do have a significant slope. Because if you reject, you now don't believe the slope is 0 anymore. I also look at the confidence interval to back me up. Notice these numbers. Notice the numbers that's not between them. 0. My confidence interval does not contain 0, so that's why I believe I have a significant linear relationship. And in fact, that come back to my big old summary at the end. Are you sure you have a significant linear relationship? You have a good model? Well, my model is only 12% predictor, but at least it's an accurate model because of 2 reasons. Part F, my confidence interval does not contain 0. If your confidence interval contains 0, there's a chance your predictions are useless. That means the relationship between these, there is none. Hey, that's a result though. Let me pause there. If your slope is 0, you're just going to say, hey, my conclusion is they're not related. You cannot relate shoe size to intelligence. Sorry, you can't do it. In this case, you can relate them because 0 is not in this interval. There's 2 reasons I build this confidence interval. 1, to show that I have a significant relationship, and I believe in my prediction. 2, to utilize the upper and lower bounds as ways to change my slope and my prediction status. I'm all about making forecast, and I can forecast using the prediction line, Or I can remove and change the slope with either one of these numbers and make either more positive predictions or lesser predictions. Your choice. All right, so second thing I want to know. The reason for the t-test, the reason for part G is for the p-value. My p-value says I reject H naught, and that means I have a non-zero slope. And that's important to me. Once again, that backs up my confidence interval. See, you see, the t-test and the confidence interval should back each other up. They work together. That's always true, no matter what you're doing. The test and the confidence interval for the same thing, of course. T-test for slope, confidence interval for slope. They got to do the same thing, okay? If you're doing t-test for mean and confidence interval for slope, that's useless. T-test for slope, confidence interval for slope should say the same thing. So they're kind of like a double check in some respects, and I love running double checks. I like making sure there's no way when I do my research somebody can say, uh-oh, but what about this? No, look at my check. My t-test for slope says I did a hypothesis test. My p-value is less than 5%, which means, according to my data, you have a very useful slope. Second thing I noticed, 0 is not in this confidence interval, which means my prediction line is pretty good. Now, by the way, I do have to put a little exclamation at the end. I only have 12% of the reason rent varies, which means if we pick another variable, it might have a higher r-squared, and that might be of more interest to me. Or let me lead you into advanced studies. Maybe two variables together, two x's together, make a higher r-squared, and that's more valuable. I like to always increase the r-squared value, the predictor variable status. I love that. The higher the r-squared, the better. But be careful. That's called the kitchen sink issue. Look at my multiple variable regression videos if you really want to jump into how can you utilize more variables to help you predict. Right now we're utilizing one variable at a time. We're in basic statistics. I do have advanced statistics videos and playlists for you to check out later. If you're wondering, these are the typical questions I would ask on any homework or project. All right, let's just summarize quickly. First thing you do is you do the assumptions. Second thing you do is you rip apart your slope, your intercept, and your r-squared. Why? Because you usually give this in your pretty picture and you present it. And when you're presenting, you want to make sure you have it code what these numbers represent. I often like to include these, and I know how to explain what these represent. The confidence interval, what it does. The t-test for slope, what it does. And reason I do this is to really make sure people understand I have a very nice equation that predicts. Now, the prediction status is not that high, but it does predict. And that's what we're looking for, a forecaster. All right, guys, thank you for watching my video. Stay tuned for others.